I want you to recall the diffraction pattern for a two-slit experiment. You've got some separation D right here, and you've got light coming in. You want to do rays or the plane fronts of the wave. Here they are, the plane fronts of the wave. And then there are waves coming out like this and waves coming out like this, right? Because of, oh, I don't know. It seems like there's somebody's principle who says that these guys, if they are the front of every wave is a point source. So here's a point source and there's a point source. All we've done is we've canceled out all the other point sources. So we've got these 2 point sources and they can interfere in a beautiful way. And we remember we got something like, if I have a screen over here, got a screen over here, and that screen then would have some peaks on it. Let me try to tack this out a little bit. Right in the middle, we're going to have a peak, and then over here a little bit at some distance up. We'll have to do some angle calculations. And then there's here, this is m equals 0. I'm going to assume this is a long distance away. L is a long distance away, and this is m is -1, and m is -2, and m is 1, etc. And we're going to have all these peaks, and so it looks like this. It looks like, woo, ready? Ready? Here we go. Big peak, slightly smaller peak, slightly smaller peak, etc. like this. And then, yeah, same thing happening up there. So these guys are all the same width for a two-slit diffraction pattern. But notice that there's like peak, and you could say there's actually a ton of light in this whole region right here. So it's not like bright dot, dim dot kind of thing. You've got a lot of light in that region and a lot of light in that region. But if we had a third slit, ready? I'm just going to set you up. But what if we had a slit there, and a slit there, and a slit there? Then they're all the same spacing apart. We're going to call that D to the center, and this is also D to the center of there, and the center there. And the light comes in, and it's like pew, pew, pew. And then we've got a source here, and a source here, and a source here. And the only thing that's going to be different about it is it's kind of going to be like emphasizing this pattern right here. And the more and more slits that we get in a row, the more emphasized this pattern will be. So I'll kind of tick this out a little bit. I'll say in the middle there's a peak, and then up here at m equals 1 and 0 and -1 and -2 and -3. We're going to get these peaks, but what we're starting to see is that they become a little bit steeper. So I'm still going to get a 0 right in between them, but they become a little bit steeper. And the 0 becomes just slightly wider. In fact, as we get more and more of these, we could have, I don't know, what do you want? 1,000 slits all in a row? Yeah, yeah. Now you're talking about diffraction gratings. And diffraction gratings are where it is. Sorry about my formatting right there. Diffraction gratings are fantastically awesome. So I'll refer you again to this cal plate. If you can get your hands on one of these, buy it used because it is awesome. Here I've got 5 different width slits, so you can experiment with that. I've also got a double slit that fades into greater and greater spacing, and then suddenly, oh, it's a single slit. You can't really see that, I'm sorry. And then it goes down to a very narrow single slit. Here I've got 5 different diffraction gratings with different spacings between the slits. And here I've got, oh man, what do I have there? Oh, 1 slit of a given distance, given width, and then 2, 3, 4, and 5 of that same width and same separation. Here I've got 1 slit, and now I've got 2 slits very close, 2 slits further, 2 slits further, and 2 slits further with the same width. Whole bunch of things that you can experiment with. I'm interested in this middle column right now because it's got diffraction gratings in it, and of course, if the spacing is really tight, watch this. I could get a diffraction grating, and it could be like, what did I do? Purple is my grating. Oh, okay, great. So I'm going to have a whole bunch of different slits right here. And the result over here on my screen is absolutely fantastic. Now I've still got a peak at m equals 0 because they're all the same distance. Nah, it's really hard to determine what's m equals 0 and what's what's m equals 1? Because this one has these two the same distance, and this one has those two the same distance, and this one has those two the same distance. Of course, this L is supposed to be really big, so I'm not proposing that the distance between these guys, which we'd probably call delta y, this distance is not at all the same as the separation distance here between the slits. So let's not get ahead of ourselves. But I do want to say that we're going to be getting these peaks here, and the peaks are really, 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 really dramatic. There is a dot here. And then some little warble, 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 and then a dot, and then you get some more warble, 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 and then a dot. So these are called the principal maxima. And then you've got this region here where there's, I guess there are several regions in the middle of perfect destructive interference, but you've got no light coming in the middle, and then you've got these spots, spot, 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 warble, 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 spot, warble, 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 spot, and you can't really tell the difference. Notice that these are all kind of the same height. So what I'm doing is when I'm shining a laser, I'm going to get a laser for you. I'm shining a laser through a diffraction grating, then I'm going to get a whole bunch of different spots. Oh no, my laser's missing. What am I going to do? Somebody actually stole my laser, so I'm kind of freaking out right now. Can I get you a blue laser, maybe? Would you like a blue laser? Watch this. Okay, here's my laser, and I'm going to shine it through a diffraction grating. Here is a diffraction grating, and I see 3 spots. But notice there's nothing in between them. There is just complete cancellation. And I can get them closer as I move this closer and closer, and further apart as I move them further and further apart. And the green laser shows that a little bit better, but that's what a diffraction grating is all about. So now, what the heck can we do with them, right? Diffraction gratings are incredibly useful. I'll bring you over here to this antique machine that I found in the back. It is designed to separate frequencies. Now, light comes in over here, comes in right here through that slit, and then it goes through this where there's absolutely nothing at all. Interesting. And then it goes through this right here. See that? That is a diffraction grating in there, and it's very, very old. In fact, it's got part of its tag coming off, and it says it has 510 lines per inch. Ooh, lines per inch, yuck. And then the user, that's you, is supposed to look through that viewpoint right there. And what we're gonna do is we're gonna look through there, and we're gonna say light comes through the slit, hits the diffraction grating, and appears to have come from a different angle depending on its wavelength. And look what's over here. What we have over here is a scale, centimeters times 10 to the negative 5th. Oh, grating constant, sorry, those are not lines per inch, sorry, it's 5,710 lines per centimeter. Oh, that's very reasonable. All right, so what we're doing here is we're actually finding the wavelength of the light based on how much it is diffracted from our diffraction grating. What fun. Let's set up this camera again and see if we can do a little bit more physics. Let's do some more physics. I have a problem set up for you, and it goes like this. Yo, when a 546 nanometer light passes through my diffraction grating, I see a second order principal maximum at 16 degrees up. How many lines per centimeter does it have? Now, I need to give you an equation for diffraction gratings because I haven't yet. But guess what? It's not a big surprise. D times sine of theta is going to give me a principal maximum when it's an integer number of wavelengths. This is the same as a double slit diffraction experiment. It's just that the principal maxima are super, super duper bright. And the cancellation regions are really, really dim because a diffraction grating is really like a whole bunch of double slit diffraction experiments all on top of each other, all reinforcing each other, so you get really awesome results. 0, plus or minus 1, plus or minus 2. Let's write this in scientific notation. We're going to have that it is an integer. Any integer, if m is an integer, then we've got ourselves a bright fringe. Now they're saying the second order principle. The second order principle, so that means m equals 2. Let's draw ourselves a picture. We've got a diffraction grating, and the grating's like this. It's like pew, 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 pew. And light's coming in. Light's coming in. How did I draw light? I think light was, oh shoot, light used to be green and that used to be purple. Well, we're flipping it all around today. Light's coming in like that, and we've got waves that are all going to interfere with each other in a really complicated way. And we've got a screen over here that's red, and this has to be a long way away. Good. And we've got an angle, and they're saying that this angle is 16 degrees. So I'm going to tick out some of these guys. This is m equals 0, this is m equals 1, this is m equals 2, and m equals 2 is where we're talking about it. And they're saying that this angle, here there is a bright spot. This angle is 16 degrees, 16.0 degrees. And we just need to do a little bit of math. Are you ready to do a little bit of math? They want to know how many lines per centimeter it has. So what if I find the separation? Separation D equals m times lambda over the sine of theta, and m's gonna be 2, so I plug all that business in, and I found that the separation between the slits is 3.96 times 10 to the negative 6 meters. Is that okay that I'm using 3 sig figs if I was given 3 sig figs right here? Yeah, and I guess second order principle probably has infinite sig figs. It is the second one, so count it, right? It's not a measurable thing, it's a countable thing. So if I know the separation distance is that big, then how many of those can I fit into, for instance, a meter? Well, this is lines separation, and I want lines per meter, so I better take the inverse of that. And I'm going to say that this number here is the number of lines per meter, and that's going to be 1 over the separation distance. I hope that's reasonable for you. That comes out to be 2.53 times 10 to the, 2.53 times 10 to the 5th lines per meter. That wasn't what they were asking. They were asking for lines per centimeter. So do we expect more lines per centimeter or fewer lines per centimeter than we have lines per meter? Well, think about that. Okay, nope, it's going to be, I'm going to write it in new units. N is 2.53 times 10 to the 3rd lines per centimeter. All right, that's the problem. Nothing to it. You can handle all these diffraction grating problems because they are really simply diffraction problems, just with a much simpler kind of diffraction.